Hey pre-calculus friends, we are in section 8.1. We're looking at geometric vectors, and we're going to start off by talking about some vocabulary. Give yourself a lot of space. The first vocabulary word that we have is the word vector, which refers to a quantity that has two aspects to it. It has both magnitude and direction. So that quantity geometrically is generally used. We use a segment. Really, it looks more like array, but a segment to represent that. So the length of the segment would be the magnitude, and the direction would literally be the direction that you see it pointing in. We often use a lowercase letter with a small arrow on top to represent a vector. Now, when we take our vector and we put it at the origin, we say that that vector is in standard position, like we are doing right now with A, vector A, and there we go. So that's what standard position would be. A zero vector has the same idea. We think of it in the same idea as having a magnitude and a direction, but when we're dealing with a zero vector, the magnitude will be 0, but the direction can be in any direction. So a zero vector, where's that? Zero vector is going to have a magnitude of 0, but a direction in any direction because it doesn't really matter. When we just going back a little bit, I wanted to highlight some things. When we are discussing our vector, we know that it has these two components, which is magnitude and direction. Often though, direction is going to be more given as an angle, especially since if we take our vector and place it in standard position, we can talk about the direction as that angle theta. So the magnitude of A would be written as kind of like the absolute value of the vector. Standard position, again, is basically taking your vector and placing it at the origin. And the zero vector, as we mentioned, having a magnitude of 0, we could write that because the magnitude would be 0. That's really the whole point of that. Okay, two vectors are equal if and only if they have two things, the same magnitude and the same direction. And two vectors are considered opposites. I'm going to talk about resultants in a minute, but two vectors are considered opposites if they have the same magnitude but exact opposite directions in opposite directions. Okay, so you want to keep that in mind. The next thing we're going to talk about is resultants. So a resultant is if you have like one vector here and you consider what happens if that vector and let's say another vector like this acts on the same object. What you want to think about is what is the result? What is the resultant? So if you think about it, one vector acts on one thing, then another vector acts on that same thing in that order, or even in the opposite order, what will be the resultant vector? And that's what I have here in purple. So this would be the resultant vector if per se I had like, I don't know, vector P and vector T. This would be considered P plus T. So we can add vectors and we can also perform other operations, and we'll talk about that. When we deal with the idea of vectors, we need to make clear that we have two different types of quantities we're dealing with. One quantity is a vector quantity, and that's kind of new to us. But what's not new to us is scalar quantities. So most things that we're used to are scalar quantities. Weight, height, just has one number, one value that we use to represent it. Mass, those are scalar quantities. Scalars generally just look like constants. Two or more vectors are considered parallel when you have their directions are exactly the same, which we're kind of used to with the concept of parallel, or if their direction is exactly opposite. So if I'm moving, I don't know, like 30 degrees, if these were in standard position, if they were both 30-degree vectors, they were running at that angle, that was their direction, then that would be considered parallel. And also, again, if I'm thinking about this in terms of the being at the standard position, if I were to refer to this angle as an angle that is So not 180 plus 30, which is going to be 210 degree. If the direction was 210 degrees, this vector would also be considered parallel. And finally, component parts is what you think of when you hear the word components, and that's exactly what it is. If I have a vector, what are the components that make up that vector? And so we can think about it in terms of when we were adding these two vectors together, we could say that these two vectors are component parts of this. We could also think about components as how far to the right we go and how far up we go in order to get to the same place. So these two vectors are considered, these two vectors that I've drawn here in purple and green, pink and green, are considered components of this black vector. All right. With all of that, let's get started with some examples. So one of the easiest questions that you will probably be working on in this section will be to figure out what the, using a ruler and a protractor to determine the magnitude in centimeters and the direction of the vector n, or whatever vector that you're given. And so really you literally are measuring this. Now I lifted this from the textbook and it's larger than the textbook. So I'm not going to say what the measure is because it will be different depending on the screen you're looking at. However, we can talk about this angle where we will be considering the angle that it makes with kind of a horizontal axis. Hopefully that's horizontal enough. I'll try again with a horizontal axis. And so you would use your protractor to measure that. But of course, I can't really demonstrate that easily on screen. So you can eyeball it and you can tell me what you think this angle is. But I'll tell you that the angle is 30 degrees. And so the length would be the magnitude and the angle would be considered the direction. We have two different methods when thinking about adding vectors, and one is considered the parallelogram method and the other is the triangle method. Here you could see if we have the component parts Q and P and we're adding them together. What we would do is with the parallelogram method, we would place their beginning points at the same point and then create a parallelogram, and the diagonal would be the sum of the two vectors. We also have the triangle method or the tip to tail method, which basically is exactly as you think it is. You're going to take one vector and then take the next vector right after it and compute the sum or the length and the direction of the resultant vector that you get. And so in example 2, we're going to be considering both of those methods as we find the sum of these two vectors, and we're going to use both of those methods. Then we're going to compare the resultant found in both methods. Okay, so these are not the exact vectors from our text just because copying and being able to move them was not going to be a thing. But here in example 2, we are asked to find the sum of vector v and vector w. So we'll do that by using the parallelogram method. So the parallelogram method, again, run up here, we're supposed to put them end to end and then draw a parallelogram and then see what the resultant diagonal would be. And so we'll do that just like you'd expect us to do it. So you can imagine that this is a little bit harder to do if you do not have like access to technology that's going to move your angles around for you or move your vectors around for you. So you have to be very careful in the way you actually draw your pictures. So now we're going to sketch out the parallelogram, and of course I am probably not going to sketch it. I'm going to just use a gray instead of a gray line instead of dotted, and I'm going to try to measure it up as best I can, and I think that's pretty decent. And then I'll do this, making sure that that seems like, no, that does not seem particularly good. So I think it'll be right here. All right, and I'll extend this a little bit. Okay, that's a little better, not perfect, but we'll make it do. And then so when we do that, this vector that I'm drawing in pink will be the resultant, and so I would write that as the sum of v and w. Okay, so that's the parallelogram method. The next one we're going to try is the triangle method, so I need my angles back. Okay, so that's a bit better. So now when we use the triangle method, what we're going to do is we are just going to take both of the vectors together, end to tip, as they say. So we'll put the v vector there, place the W vector right here, and then you notice that we will just connect the end and the tip together, the end of the first one to the tip of the last one, and you see that we get that value here, which looks to be the same vector. Let's scooch up like that, which looks to be the same vector that we got before. I'm not going to measure the angles right now. I'm not going to measure the lengths just because it's not going to coincide with what you might see on the screen anyway in terms of the length anyway. So, but you can see pretty well that we have the same value. You might be wondering if you were to start off with this method, but if you were to first grab the W ray or the stop. But if I put this here, will I get the same vector? That's really the question that I want to answer. And you'll see yes. So it doesn't matter the order. Notice that we get all three of these pink lines look the same. Doesn't matter the order. You just got to make sure you know what you're doing, not like I was doing there. And that when you do the triangle method, it's end to tip. And when you do the parallelogram method, you start them both at the same end. So we're comparing them. Everything looks good. We're feeling good about the work that we have done. So this example refers to the example in the beginning of the text. Here's what we're dealing with. We have a situation where an advanced glider known as a sailplane has a high maneuverability and glide capabilities. The Ventons 2B, a sailplane, placed at first at the World Soaring Contest in New Zealand. At one competition, a sailplane traveled forward 8 meters per second and it descended at a rate of 4 meters per second. So if we want to think of those two bits of information, those two quantities as vectors, we might want to draw them like this. So you notice that this vector, the one that I just labeled F for forward and this one D for down, this vector is twice the length of this vector. Just as this relationship indicated here, we've got 8 meters per second in one direction and then 4 meters per second in the other direction. Determine the magnitude of the resultant velocity of the sailplane. So what we know is that we can consider doing this in either of the two forms. We can do it in the triangle form, or we could do it in the parallelogram form. I'm kind of partial to the triangle form, so I feel like doing that method. And so we know we're going to start at one end and do tip to tail kind of thing. And then so our resultant vector is going to be this here. And so when we calculate that, how do we calculate the magnitude? Maybe we can calculate the direction, but we definitely would need the magnitude first. What we'll do is we will recognize this as 8. We'll consider this a length of 8. We'll consider this side a length of 4. And now as you look at it, you're like, yeah, clearly Pythagorean theorem. So we know that this pink side is going to have a length of, I'm blanking. Oh yeah, 4 root 5. I wanted to write 5 root 4, but I kept thinking 25 is not in there. So that's why I'm like dawdling. So 4 root 5 would be the magnitude. I guess thinking about the square root of 80, you know that that would be close to 9, right? So 8.9 or 8.8 something something is what that magnitude would be. So here in example 4, we're going to use the triangle method to add up these two vectors. And these are made up vectors that I have that are similar to the ones in the text, but they are not the same. So here's what we have. We have 2v, and then we have -1/2 w. So there's a whole lot going on here. Let's think about what that means. This 2 is considered a scalar, and so 2 times v would double the magnitude and have nothing to do with the direction. So basically, if we're thinking about the vector 2v would look like this, which is not hard to anticipate. It's double the length. So that's our 2v. Now, -1/2 w, or vector w, is going to be a little bit different. You probably guessed that it would be half the length, but what's going to happen with this negative, that's what we're going to see in a moment. So -1/2 w is going to be half. Let's see if I can get it to come off. It won't, but that's okay. It's going to be half of w. So let me erase parts of w that I can. There we go. It's going to be half of w but going in a completely different direction. So these are the two vectors that we're dealing with, and we're going to do the triangle method with these two. So triangle method requires us to go end to tip, and so we'll take this, we're going to go end to tip, and then our magnitude and direction can be seen in this resultant vector. So this is going to be 2v 2 times vector v minus 1/2 vector w. In example 5, we see a ship leaving port that sails 75 miles in the direction of 35 degrees north, due east. Find the magnitude of the vertical and horizontal components. So if we think of this in standard form, we'll start at the origin and we will consider the path of the ship to be something like this. All right, I think that's around 35 degrees. Okay, and so we know that this vector, the ship's vector, is going to be considered having a direction of 35 degrees and having a magnitude of 75. And so with that in mind, when we think about the components, what we're thinking about are the values, what we're really thinking about the displacement north and the displacement to the right over here. So we're really calculating x and we're really calculating y as the component values, as those component vectors. So to do that, we need to keep in mind that this angle is 35 degrees. We also need to keep in mind that we're going to kind of consider this a length of 75. And if that's the case, you can see that some of your right triangle trig needs to come back into play. These are the two equations or relationships that I think are going to be most helpful for us. So sine of 35 is y opposite over hypotenuse, cosine is x over 75. Therefore, y is equal to 75 sine theta, sine of 35 degrees, and x is equal to 75 times the cosine of 35. And so you got to go grab your calculator, and once you do that, you'll get that y is approximately equal to 43 miles and x is approximately equal to 61. So in example 6, we have a piling from a high-rise building is pushed by 2 bulldozers at exactly the same time. One bulldozer exerts a force of 1,550 pounds in a westerly direction, and that'll be this one. And then the other bulldozer pushes the piling with a force of 3,050 pounds in a northerly direction. So you can see x refers to the westerly direction, y refers to the northerly direction. What is the magnitude of the resultant force upon the piling to the nearest 10 pounds? And so we know that that resultant force or that resultant vector, oh, thank you for straightening up. We see that that resultant vector will be this. We want to know what the magnitude of this vector is. And so basically we're searching for this. We know that this is just Pythagorean theorem. So whatever this squared is plus this squared square root is going to give us our value. So we know that this is going to be 1,550 quantity squared plus 3050 quantity squared square root. And when we get our calculators, our magnitude will be somewhere around 3,421. So that's part A. Part B asks us, what is the direction of the resulting force upon the piling to the nearest 10 pounds? So the nearest, what is the direction of the resultant force of the piling to the nearest 10 pounds? That's weird. Because the direction is not given in pounds. So I'm wondering if this is a typo as I look at that. And when we talk about directions, we generally want to find the angle. So that's what I'm going with here. The pounds, I'm not sure what's happening. So since we're looking, we need to figure out what this angle is. We are going to use what we have to get what we want. And we have, in reference to this angle, the adjacent and the opposite, which seems to imply we should use tangent. So tangent of theta is going to be equal to opposite over adjacent, 3050 over 1550. And then we know that what we'll do is we'll take the inverse tan or arctan, and that requires a grab of the calculator in order to get, and when we use our calculator, we'll get that this angle is about 63 degrees right here. So that's theta, and that's fine. However, since we are dealing with kind of a real life situation and we're not anchored at the origin or anything like that, we need to consider our direction in reference to north, south, east, and west. Okay, so I'm going to just draw like a little, kind of like an axis here, but I want you to think about each of these as directions: north, south, east, and west. All right, so we've got north. That's an A. Thank you. We've got north, south, east over there, and west over here. Okay, you know what I'm talking about, y'all. Y'all allow me to do the thing. So the way you'll see the answer, the textbook answer, it would not be 63 degrees, nor would it be considering standard position, adding the first quadrant and to the 63 degrees, or subtracting it from the second quadrant, 180 minus 63 degrees, to get like 117 or something like that, which would make sense to me. But if we think about it in terms of directional, we would say that this resultant is, watch now, 27 degrees due west of north. I know 63 degrees is the angle, but what that implies, given the direction, is that this vector has a direction of 27 degrees due west of north. I hope that made sense, sort of. All right, look, I'm gonna let you guys go. It has been a long video and a lot to take in. Take your time with the notes, take your time with the section, and I look forward to talking to you all soon. Bye-bye.